la doctora Victoria Vampa, la cual estaría arrancando ahorita y tendría hasta más o menos las 9:40 para poder elaborar la presentación. La profesora Victoria Vampa es doctora en matemática, tiene también una maestría en simulación numérica y control y licenciatura en matemática aplicada y análisis de sistemas, y trabaja en la Facultad de Ingeniería de la Universidad Nacional de La Plata, si mal no estoy. La profesora Victoria nos va a hablar sobre el tema de Using Information Theory to qualify to characterize the COVID-19 through time series data. Profesora, no sé si...
¿Puedo compartir? A ver.
Adelante, probemos si puede compartir, por favor. Estamos viendo ahorita su navegador. Ahora sí estamos viendo el PDF, nada más si lo puede poner en pantalla completa.
¿Está bien?
Perfecto, yo lo veo bien, el resto de ustedes me imagino que también lo ve bien. Adelante, profesora.
Well, I prepare in English to speak. I don't know what in your opinion, or tell me, I don't know. Javier, you suggest me to speak in English because of the audience.
Yes, I think it's better because we have some colleagues that do not speak fluent Spanish.
Okay. This research work was carried out with, I am Victoria Vampa, with Andrés Kowalski, Federico Jolic, Marcelo Rosada, and Mariela Portesi from the University of La Plata, from Argentina. I want to thank Javier for your invitation, and for me it's a pleasure to stay here with you. Well, these things are known, but I want to remark what happened with numbers, because when I sent the abstract to this event in September, we have 234 million cases of infected individuals and almost 5 million deaths. And nowadays, we have the double of infected cases, and fortunately, not the double of deaths, but we have nearly 6 million, and that was the effect of vaccination, due to vaccination. In this work, we study the time series corresponding to daily infected and daily deaths, and we use information theory quantifiers mainly to evaluate the unpredictability and disorder in those time series. And in this way, we want to contribute to a better understanding of the dynamics of the pandemic. I'm going to tell you in an introduction of this research, the information theory quantifiers we use. One is the permutation entropy and the other wavelet entropy, and how we do the rolling window analysis of that time series. We also make something with wavelet coherence and some conclusions of our research. I want to tell you that my research area is not epidemiology. I work in signal processing, in particular in ECG signals. And when started the pandemic, a friend of mine phoned me and asked me, she's a physician working at an Argentinian hospital. She asked me whether it was possible to predict the number of beds and intensive care units occupied in the short and mid terms using mathematical models. She asked me, she was desesperated, and she thinks, well, can you help me? And then I started analyzing the exponential growth, the double doubling time of the disease that you know, and different epidemiology models. And one is that appeared is the SIR model that it was designed 100 years ago, but is important to use at first time. And with this, we wrote an article about this model and with numbers of infected cases from Argentina. In a second stage, we study another thing with the same co-authors that we did this work about the correlation, especially the correlation between the number of cases and deaths with the increase in mobility and attendance to workplaces. When we were asked to make this, when in Argentina, we have a peak very important in April 2021. And then our conclusion, it was that the onset on face-to-face classes had contributed significantly to the spread of the virus, and especially in the province of Buenos Aires and the AMBA region that is around Cava, and consequently in other regions of the country. But you know that scientists are contributing to understanding of this pandemic, that mathematical models are very important. They provide a powerful insight on how complex systems behave, and this enhances the capability of developing control and prevention policies. The power of mathematical tools is increasing with the help of computers, and the availability of data is growing, but the thing is how to interpret data to development of effective containment or mitigation interventions. What we do is to apply information theory quantifiers that have been useful to characterize this thing is the informational content of time series. That is the main thing. We analyze appealing to different information measures, in particular entropic measures, and to gain a better understanding of its dynamics. You know that many works have focused in trying to model the dynamics, obtaining a reasonable degree of accuracy, but the thing is how to predict the behavior. That remains a challenge in several respects. In this point, I want to remark that is another point of view to study the time series, that is analyzing the content of information, and not by solving differential equations, as was presented before, is another point of view. And also, you know that you have differential equations, deterministic or stochastic, that's different models. We want to define, to calculate the entropy, the permutation entropy, we have to have a probability distribution. How is built? This is due to Van and Pompey. It has 20 years ago. And you have to define two parameters, the embedding dimension and the time delay. And the thing is this, you take d values, one of the parameters of the time series, and you assign one of the ordinal patterns that you can have when you do the permutations of the numbers 1 to d. An example is very simple. For d equal 3, you have 6 permutations, and these are the 6 possibilities. And then you take 3 numbers of your series and you assign one of the patterns. For instance, if this is decreasing, you assign the pattern is 3 to 1, that is the type 1. In this way, in this case, you have these numbers. At 8 is in the second place. Here you have to put 2, following by 3, because 9 is in the third place, and 1 because 10, that is the higher value, is in the first place. So this is type 3, corresponding to the 6th permutation. How you define the probability distribution? You count how many times appear each of the 6 types in this example. So you have 6 values, and you count all the possibilities. You have a distribution, a probability distribution, and in this way you can calculate the permutation entropy. Is a concept important defined by Shannon in 1948, and this is what you obtain. If you have, I want to put a signal like this to see what you know, what you see. This is a signal that you have different frequencies, and you know that Fourier tells us that information about different frequencies, but not the time in which it occurs, the change of frequencies. And the thing is, we are going to treat not all the signal, but only a window. That also you define in this way, you define a length of the window, and you take a portion of the signal. So you can obtain the value of this permutation entropy, for example, for this window. As you see, is increasing. It have intervals where it's increasing or later decreasing. So the patterns of the 6 possibilities that appear more frequently, and the first and the last, which correspond to 1 to 3 and 3 to 1. And if you calculate the entropy, it has a half. And you see that you have a normalized entropy, so you have the higher value is 1, and that means that you have you don't know anything about this. You have the entropy has at its higher value. What happens if you add a white noise? Then your signal is like this. And so now everything changed because it's not increasing or decreasing in intervals. So the patterns are different here. And so you have a probability distribution near to the uniform distribution, that it has the entropy with value 1. So you see here that is almost 1, and is very random, to say in a way, the signal. Then this quantifier is very important. Gives a measure of the disorder of the time series. Also detect causal relationships, and here I explain what about if it's increasing always, then the entropy is 0. And when and this can be interpreted as follows: if the time series is monotonous, then its behavior is predictable, and as such it has a low entropy, and it is 0. Then for the example, we saw that the main contribution of this entropy comes when you have fluctuation. And another thing important is that when your series is constant, you have to, by convention, you assume that you have an order, this inequality that is less than the following. And with this convention, if a time series is constant, its distribution is maximally peaked and the entropy is 0. What about the other information theory quantifier? This is based on a wavelet analysis. I don't know if you know about this. Wavelet analysis is comes to how can I say, to do what Fourier does not give us, and give information about time and frequency. So if you apply the discrete wavelet transform to this signal, you have this representation. The scale is the inverse of frequency, so you have here corresponding to this low frequency, and in the other half of the signal you have the contents of these lower frequencies. And these are the absolute value of the coefficient corresponding to this decomposition. Well, how we can define a probability distribution? Well, we have with the discrete wavelet transform a representation of a signal, and if the decomposition is carried overall resolution levels, we have this expression. And what are these? These are the coefficients that it were in the figure, but and these are functions that correspond to a wavelet family, and these indexes correspond to translations and dilations. Because dilation is the J index that have to be with the scale, and translations is the K. And then you have this representation, and this is a phi of t is a mother wavelet that you can choose. For example, these are two mother wavelets or two families. The Mexican hat is used frequently in the continuous wavelet transform, and the family of Daubechies wavelet, they are used a lot in many applications because it's a family that has very good properties as orthogonality. And this is, for example, Daubechies 6, but it has to be the order with the coefficients. How to build the distribution probability is with this coefficient, because when you have to calculate this coefficient, you have to do the inner product between, as Fourier, very similar, the signal and scale and shift versions of the mother wavelet. I try to make these figures to understand that they are different scales, so you have to do the inner product. And then you can do in every levels or scales that has that are related to the number of values your signal has, to the length of the signal. In this sense, you can calculate the wavelet energy considering only the scale J, and also a total energy. And with this, you can define relative energies, and with these relative energies, you can build the distribution probability you need to define the other quantifier. It is very similar to the permutation entropy. So we have the second quantifier, and if we do the same with the same window, you can calculate here, it has to be with the energy in each level. You have 8 because the length of the window, it was 256, that is the power of 2 is 8. And you have more than a half, but no so higher the entropy. When you add white noise, in this case, the same we did with the other quantifier, we have no changes. This quantifier it does not detect the small oscillations or fluctuations. Then we have defined the two quantifiers, and the thing is how they are used. Well, we are going to work with windows. The name is rolling windows because we go with time, defining new windows, and in this way we can study their variation in time. For each window, we obtain the distribution, the probability distributions, and we study the mean values of permutation and wavelet entropy. One thing to remark is that the entropy decreases when curves are smooth, as we see, where there is no noise or they are smooth. So the rolling windows behave like this. We define a length fixed, and then you move by one value. So you have a lot of windows, and you study for each window these quantifiers. This is a technique known to study how the stages of evolution of the variables of interest, and then you calculate what we note in this way, permutation and wavelet entropies for each interval. The first, as we say, takes account of causality, while the second was based in wavelet decomposition. And then you can study these quantifiers as a function of the index J, or the different intervals or windows. The thing is, what about fluctuations? Because we see that they are important. One may wonder whether the entropy would be smaller by getting rid of fluctuations or smoothing the curves. So what is the correct to do? One possibility is to use moving average that replace a given value of the random variable by the mean of an interval centered in that point. The thing, I don't know if you visit this place in our wedding data, that is a free publication which is updated daily. A moving average with L7 is used because of data are recalled in a different way on weekends. So if you take this value, it's not affected. There is no changes with the values of the weekend. Yes, it is important to know that if L is increased, you have fluctuations tend to disappear. We apply the rolling window method to study the variation in time of these quantifiers for both curves of daily infected and daily cases for every country. And it's important to note also that the dynamics of the time series depends on how the collection data is done. And for this reason, some countries exhibit a somewhat atypical behavior, as China, for example. And also we know that these mean values change. I put first the the curves of your country to see what happened when we calculate these quantifiers for the windows. And we have high values. We consider high values when are higher than a half. And these curves are similar to Argentine, where also the entropy takes both quantifiers take high values. Australia is atypical because of the infected cases have a peak in this January. China is the opposite because here we have very few cases, but always these entropy quantifiers give high values or higher than a half. Also the same happened with developed countries or developing countries as South Africa. And we study this, the mean values, and in this case, I consider L1 that is without smoothing, without the moving average, and you see that they are very high and almost 1, both entropy, mean entropies for both quantifiers, permutation entropy and wavelet entropy. And if you take L7 a week, you have lower values in both cases. The same we did, but I present only 2 cases, United Kingdom and the United States, with death, with daily death. And we studied that the entropy is in general with lower values than the case of the infected cases. The other thing, well, this is the application of entropy quantifiers. Now I want to add another thing that we were studying, that is, what about the correlation between time series, as we did between the mobility and the cases for the report we did. We analyzed the correlation between infected cases and death. And we see that they were correlated until vaccination appeared. And it was interesting to have this information. I don't know if you know what wavelet coherence is, but it is based in the representation I presented in time frequency for the both series you want to study, and the wavelet coherence detects the frequency that are in common. I don't know if I am clear with this, but you can ask me later about this. So which frequencies appear in both time series? If first I put Costa Rica, you see, this is the analysis we do to see the new cases and see new deaths, and this is the wavelet coherence that is in frequency and time. And then as we have 2 years, the first year is the middle of the half of the figure. And then you can see that the yellow shows that these exists correlation between these 2 curves. Also here, Australia is different because the correlation appears here because they both have a peak. The curves, both curves. And Indonesia is different also because you see that it remains correlated, both curves. South America, here you can see that is more blue in this half, indicated about the effect of vaccination. Africa also, and the word here is a good resume that you see that the effect of vaccination, it can be because here is more blue. I want to put this to remember, I don't say to have in mind, I don't know, what happened with vaccination during the last year, what it has changed in all the world, and what important it was. Well, and then is what I have to tell you. We have applied different information quantifiers. Our contribution extends previous works and adds new aspects. We analyze with rolling windows. We analyze if it is convenient or not to smooth the curves, and if you lack the information, if you do that. And the conclusion is that the mean values of the entropic quantifiers are high, even they are smooth. And that is what confirms that you have lack of information, you are almost with a random series, and then it is why it is so difficult to predict what happened with this pandemic. And also we study the correlation or interdependence of the acquired data. We are working now in how we can quantify this correlation. And in this, comparing different countries, we see that it was very important, the vaccination, as I told you. And also, as a whole, our results indicate that these quantifiers yields interesting clues to understand the unpredictable behavior of the time series associated with COVID-19 pandemic. Well, and that's all. Thanks for your attention. Nothing else. And this is the articles I use, and this is the work we wrote with the same cause of this work.
Muchísimas gracias, Victoria. Excelente la presentación. No sé si tendrán alguna duda o consulta los que nos acompañan en la sala.
Sí, yo la verdad no entendí una buena parte porque no manejo el tema de las ondeletas, wavelets, pero me parece, sí me pareció una herramienta útil para entender algunas cosas, ¿verdad? Que a veces en los modelos que ocasiones usamos no queda bien reflejado, ¿verdad? Los cambios, y me llama mucho la atención pues el hecho de que esa herramienta, digamos que es más propia como del análisis numérico, de la teoría de señal, etcétera, pues aquí aplicada a series de tiempo haya dado tan buenos resultados.
Sí, en realidad el análisis wavelet tiene ese poder tan interesante de aportarnos para cosas no estacionarias lo que Fourier no te da, o sea que te da esa representación tiempo-frecuencia que es muy útil porque sirve en la parte de, por ejemplo, yo trabajo con señales de ya estaba en castellano, me fui al español. In ECG signals, you can study also frequencies, and you have a wavelet decomposition that is allowed to detect diseases, infarction, perhaps, for instance. So it is a very, very useful tool, wavelet analysis. And here we use in this way to define another quantifier. Also, there is the complexity also. You can calculate from a time series. All these things comes from information theory and entropy, and this you have with wavelets. With the energy, you can calculate with the wavelet decomposition. The thing is that you can have a probability distribution, so you can use the entropy. You understand?
Mm-hmm. Mm-hmm. Yeah. Yeah. Good.
Muchas gracias. Tenemos una consulta de Freddy. Tal vez con esto cerramos el espacio para cumplir la agenda, ir al receso y después volver al siguiente bloque.
Hi, Victoria. I have just a quick question. Could you please go back to the slide where there are the references, please? I find this very interesting, and I would like to know, maybe not now because we're kind of running out of time, but probably later, Victoria, I would like to ask you a couple of questions to you regarding, maybe by email, regarding some of the applications and extracting some like sub-signals that we could use to get some interpretability of the curves related to the COVID. Like, I don't know if you have tried to combine like several signals and try to extract the wavelet information of those signals and see how does that look and what kind of information can we extract. Like if we have like a train of vector signals and then try to apply like a wavelet decomposition to the composite. It's just, I'm really interested in extracting that kind of information. And I was thinking like something like blind source, information decomposition or stuff like that. But looking at your results, it looks very inspiring and very interesting. And I would like to look from a somehow related perspective. So I will read this document you posted, and I will keep on asking some questions regarding.
Yes,
thank you, Victoria.
Yes, you can write to me, and I can give you my mail. Yes, sure.
Awesome. Thank you, Victoria.
I write here in the chat my mail.
Muchísimas gracias. Creo que we are run out of time, so I would like to thank you all for this presentation, and we are going to a coffee breakup, I think, and we will resume by 10 p.m. Nos vamos a un receso y creo que regresamos a las 10 con el siguiente bloque. El link se mantiene igual, ¿verdad?